everybody. It's lovely to see you at Imperial. I recognise a lot of faces from yesterday. And this is the informal, more techie part of the meeting. And I don't know about you, I've relaxed. I sort of feel home and in relaxed mode now. So please, when people are speaking, feel free to interrupt. And, you know, turn this into a proper interaction. It's much easier with the raked seats. This room is lovely. Even you don't have to use mics. But we are streaming, so because we're streaming, please use the mics anyway. The day is basically a sequence of talks. At the end, we're going to a bar in Imperial where basically we give you one drink, but it's a cash bar and you can stay as long as you want. And it's an informal way for everybody to keep chit-chatting to each other. I would like to introduce Cliff Jones, who will take charge of the first session.
Thank you, Philippa. I was given the opportunity to chair this session quite late on. So I'm going to be very brief and introduce our first speaker, Peter Sewell.
Thank you. So, I'm going to talk about mainstream systems and the rigorous engineering thereof. John talked the day before yesterday about the geological accumulation of infrastructure that we have. Of stacks of hardware and compilers and operating systems and what have you. And I thought it would be maybe useful to emphasize that this is a very rosy view of the world. This is a very tidy picture with, at least on my laptop, nice pastel colors. In fact, these systems are built not exactly over geological time, but over very long time periods by terribly ingenious people working under all manner of constraints. So, lest we fool ourselves, maybe a more accurate way of describing the situation is something a bit more like this.
I'm really sorry, I'm going to try and sort out lights. Keep going.
A more accurate way of describing the situation is something like this, in which you can see, well, you can't because of the lights, you can see more or less there's some hardware down here. I think this is a big pile of silicon, and this I think is probably the phases of a C compiler. There's a file system here inside these jars. JavaScript lives inside this box. That's relatively well contained, that part. TLS stack, TCP, piece belonging to the NSA over here, web browser, and you could turn off that light, and that would be good. Because if you have it really bright, then I'm going to stand over here anyway, so it's not going to help. So faced with this delightful complexity, what can we possibly do? Well, we've been doing semantics for the last 70 years or so surely we should be able to do something useful. In that, there are quite a lot of different kinds of useful ways that one could respond to this. So I thought I would start by just mentioning some of those options. And another thing that we have to bear in mind, that is a new aspect of technology which I have not previously experienced, and clearly a verification target for some PhD student. There's a lot of things that we might do. We might do full verification, except that, as we know, we can't remotely do full verification for all of this stack. It is still much too hard for us. We might aim at redesigning a clean slate stack, and we should surely study how we can do that, but getting it deployed is a little bit of a headache. And indeed, I don't think I could claim that I would know how to design a clean slate stack without reproducing either these mistakes or a whole set of new mistakes, probably both. Right. We might reason about idealized models. So we do this a lot in programming language design, right? We invent some clever new type system ideas, we prove some things about a cut-down version of them, and then we throw them into the type system of Haskell or OCaml or something without attempting to lift up that proof. So the verification is useful in design, but doesn't actually apply to the artifact that we use. We might, and indeed I think this is the most useful thing we could possibly do, use 1980s programming languages instead of 1970s programming languages. Right? And 80s, not 90s here for the JavaScript people in the audience. Right?
So this means you want C++ instead of C?
No, this means I want Camel Light. I want Camel Light. So this, I think, would be the biggest change, the most useful, easiest change that we could possibly make. But deployment is, again, a bit of an issue. If we are determined to use 1970s languages or 1990s languages, then, as Peter was describing, we can use sophisticated bug-finding analysis tools, and that's very useful, very clever, and certainly applicable to real systems, but usually only capturing quite lightweight properties. Right? Then the missing gap here that I want to focus on is the possibility not of doing really verification in any serious way, but merely attempting to understand what the interfaces are between these ghastly pieces here. So I'm just focused on the lines. Something else we have to understand is that systems are made by a testing-based process, always, almost. And so whatever we do, if we're concerned with deployment, has to be able to fit in with that one way or another. So these interfaces, architectures and programming languages and OS APIs. So within this REMS project that I wibbled about on Monday for a couple of minutes, there are people looking at a whole variety of these. There's also other work going on program logics, on some of the CakeML work, some other things I'm not going to talk about. Let me just talk about these. And let me especially focus, as there was a certain amount of complaining in the last couple of days about industry and academia and industry. Let me focus on some models of interaction which are possibly not the ones that you're used to, but which have demonstrably worked for us and for them. So if we're building models, the first thing that we need to do is understand what's the point. Right? And the point is not to produce PhD theses full of beautifully latexed models. Right? That has historically sometimes been the point, but it's not now. And there are several different points that one might focus on. So the simplest possible point is just on making some bridge from the reality of the systems that we use to the mathematical world in which we want to reason. So if we take as an example, say we want to model the sequential aspects of the fragment of x86 that we use as the target of a compiler. Right? So this is a nice, relatively simple world. Right? No complicated interrupts, maybe no floating points, quite small, models quite concrete, everything's almost deterministic. And in this situation, the vendor specifications pretty much describe what the actual physical artifacts are doing. Right? Although I have found at least one 9-bit byte in Intel documentation, but pretty much they're good here. So in this situation, modeling is just bridging this gap from reality to mathematical world. It's still not completely trivial. Right? To do this well, we need some empirical testing to validate the model, and for that, the model has to be executable, but not executable as an implementation. It has to be executable as a test oracle. So given some test program and some possibly experimentally observed result of executing that, we have to be able to decide whether that is allowed by the model or not. And then we need maybe some craft to choose good mathematical structure and to make it a reusable model. I think probably at least half a dozen people in this room have built an x86 model at some point, some of them several times. it's kind of stupid for us to keep on doing that. Okay, so here, this is like the minimal application, the minimal point of modeling. Nothing else is going to be that simple. So let me start now with modeling IBM POWER and ARM concurrency, which a group of us have been doing for the last quite a few years. So what are we trying to model here? We're trying to model the architectures. So what's an architecture? It's an envelope of allowed behavior. It's not a particular implementation. And it's the envelope which the processor vendor would like to guarantee all of their implementations will lie within, the purported programming model. And architecture is made by architects. Sounds simple, but this is really important, right? So architects are a very small group of people who are, on the whole, very clever and rather sensible, mostly, and are in control, more or less, of their architectures. Right? They have some authority to decide what this envelope is. Right? An architect is someone who can decide whether an observed behavior is a processor bug or not, fundamentally. Yeah? So this gives us, this is a lovely situation for us as mathematically minded academics, because it gives us a lever on the world. Right? If we can affect the architects and thereby the architecture, we can make things better for a whole lot of people. We have to figure out how to work with them. Right? And working with architects is a non-trivial challenge, which we have studied carefully over the last 8 years. First, one has to get their attention. And getting their attention is, for example, done by finding bugs in the processors that they are shipping. Or serious problems in their architecture text. Both of those work. Learning how to communicate with them is maybe harder. So these people are, on the whole, not going to be happy if you say, here, read my model. What we mostly do is communicate in terms of like key examples that illustrate particular phenomena. We build web interfaces for models that they can play with. We build large suites of test cases that find bugs. We build test harnesses that find bugs. Just after multiple years, we might start saying, here, look at this English version of our mathematical model, and let's go through that point by point. And we have done that, but it takes a long time to even get to that point. Right? And we have only now started to get to the point where we say, here, we will sit down with you and discuss the actual mathematical model, and maybe you will write some of it. And indeed, there may be people in this room who are doing that from one of these processor vendors. We have to do that. It's a bit delicate sometimes. Have to do that. So then what does it mean to succeed here? What does it mean for an architecture to be good? So there's a lower bound, a very simple lower bound, which is that it has to admit the behavior of the real implementations, the current real implementations, except in the cases where those have bugs. The upper bound is not so clear. So it has to be strong enough to program against. But people don't test their programs by running them against the architecture, because we don't yet have the technology to do that at scale. Right? So what we can do, and what's been very useful, is to at least test by proving that the C and C++ concurrency model is implementable above our formal architecture models. Right? So that's often been very fruitful. Right? Then there are other issues. So both IBM and ARM have other companies that build processors to those architectures, and they have to be responsive to the concerns of those companies. So that some other vendor might be saying, I imagine that I want to build a processor like this, and that means that this behavior should be allowed in the architecture, even though they haven't yet built such a thing. And then it's not just the extensional properties of the model that matter. The intentional structure of it also matters. It has to be in a form that they can understand and in a form that won't be confusing to their hardware partners. Right? So it has to, in the end, have some kind of microarchitectural feel to it, even though it's absolutely not a particular implementation. So that's a whole rather large set of constraints here. And where are we now? So we've done this for quite large fragments of the concurrency model and the ISA of both of these architectures. We've worked quite closely with senior architects and their colleagues in both companies. We have agreement, as I mentioned the other day, to release Alistair Reed and his colleagues' full ISA specification in a slightly sanitized version. So this is linking an internal processor vendor model to the outside world that enables verification for, in some sense, the first time. But there's still a whole lot of open questions. And our work is mostly not at all focused on verification. We're still at the point of understanding what the model should be.
Excuse me. So this agreement to release this version,
Yep.
how did you get that?
We talked to, so we had motivation partly because of the success of the concurrency work, both from us and within ARM. We had a clear sense within some parts of ARM that this would be a good thing several years ago, and we spent somewhat more than 2 years talking with various bits of ARM legal and university relations with very strong support at a very senior level inside ARM. It's not a trivial activity.
Peter, is it fair to say that you have done lots of verification between layers of your various formalisms?
No.
No.
We've done some. So we've done these proofs of C11 implementability with respect to these. We've done some proofs of, so we adapted an earlier version of Concert to x86 concurrency. But for these, on the whole, no.
Now we've gone through the process of getting this agreement, will it be easier next time for a different company? Or is it actually absolutely is?
Come back and ask me in a couple of years. Or indeed, turn around and later, during his talk time, rather than my talk time, ask Warren about the situation for x86. And ask Anna whether Centaur will be happy to release a model anytime soon. Okay. Let me look at some other models where the situation is different. So Mark talked about C++ 11 concurrency, right? Where, again, a large group of people in many places have worked on this over the last few years. Here again, we had an excellent lever. The concurrency subgroup of the ISO's C++ committee is a small group of expert people who are very happy to pay attention as soon as we could figure out how to communicate with them. And again, that's a non-trivial thing. If you rock up to the ISO working group and you say, even by accident, as we did the first time that Mark and I went along to this thing, by accident we put up a slide with some first-order logic on it. And we got accused of perpetrating Greek symbols, and they weren't happy. Right? So you have to be a bit cautious there. In this case, the specification is in advance of implementation. So that's good in some ways, because it's not polluted by lots of crazy historical nonsense, but interestingly different in that here we couldn't use testing of implementations as part of the process of developing a specification. Look at C as a whole, not its concurrency model. So now we move into a much more, how should I say, a much more queasy-making situation. Right? So C is still at the heart of pretty much all of our infrastructure. And there is a standard. There's a lovely ISO standard. And then there's the de facto standards of the particular semantics that different compilers implement. And then there's the de facto standards, I use plurals very carefully here, of the assumptions that systems code makes implicitly. And then there are the de facto standards of what compiler writers think they implement, and the de facto standards of what systems programmers think they're assuming. And all of these, big surprise, are different. And they're also rather hard to investigate. So this is more of a mess. And Caven and Kinderlin and some of these other people have been trying to make sense of this to the extent that we possibly can. And next week, I won't be at the LFCS 30 meeting, to my great sadness, because there's a WG14 committee meeting in London where Caven and I will be trying to see what we can do. Moving up the stack a bit. So people have talked about C, and we have the CompCert verified C compiler and a whole bunch of analysis tools for C in the world. But one of the other hidden elephants, in some sense, the job in REMS, our chosen task in REMS is to go out and find the elephants that Kathleen was talking of and make friends with them. One of the other elephants is linking. Linking is fabulously complicated and intricate and used for all manner of things. And Stephen Kell and Dominic Mulligan have been looking at that, and Dom's going to talk about that for 5 minutes later. There again, there is no central authority. There is accumulated de facto standards, really. Look at higher up the stack. If we look at file systems, so Tom Ridge and his colleagues in Leicester and David Sheets and other Cambridge Systems guys have put in a lot of effort to build a model of POSIX file system behavior. Covers by no means everything, but quite a lot of the behavior of POSIX. And this is a place where I want to emphasize that building models in ways that let one reasonably efficiently test implementations against models is a key thing here. So they've built their semantics in a way that lets you test large numbers of interesting tests on a target file system in 5 minutes, not, as we did for TCP a decade ago, in 3 weeks. And this is a big difference, right? 3 weeks is beyond dinner time, and 5 minutes is less time than it takes you to decide that you want a cup of coffee. And they've done this in a very serious way and tested umpteen real-world file system configurations and found lots of differences. So these are accumulated technical debt. Many of these differences are sort of incidental. They're not required for the designs in any way. They just accumulated over the years because people have had no way to test the behavior of the file systems that they've implemented. But here we can provide, at least for file systems which are behaviorally quite a lot like the particular main file systems that these people have specified, a turnkey tool that can be used by developers on a very attractive timescale to identify differences. Further higher up, well, I don't know, sideways maybe. So Cedric was talking about MyTLS. So I'd like to mention also, so MyTLS is focused on verification of the TLS protocol, which is a fine and extremely valuable thing. A more lightweight approach has been taken by David Kaliper-Mershiniak and Hannes Mehnert, who have been building what is simultaneously an implementation with reasonable performance and something that can be used as one of these test oracles, something that can check traces of other implementations. It's not aimed at verification, but it is providing a usable implementation, and they're also engaged quite strongly with the TLS design of future versions. So now let me reflect for 5 minutes, plus 2.5, about all of these. It's a Philippa event, right? So this is a selection. This is by no means, well, in some sense, this is not at all typical software. So for some of the industrial complaining that we heard a couple of days ago, this is totally useless. These are not methods which are applicable to building new software in a large pile of Ada, let's say. But these are some particular abstractions which we depend on in almost everything we do. And they're relatively stable over time. Right? Like none of these things have been well, except TLS 1.3 maybe, have been invented in the last couple of years. Mostly they were invented 40 years ago, God help us all. In each case, there's a real question about what the abstraction actually is. And that turns out to be the main piece of work. Right? If we knew, if there was a perfectly coherent prose definition of the ARM concurrency architecture when we started, then we could have just written that down in 6 months. It takes 5+ years and it's still ongoing because what the abstraction is, what it should be, is a real piece of work. In each case, there are multiple implementations, and that motivates having an independent spec that you can test against. And in each case, those specs are demonstrably useful to industry and to academia already. And they support also some verification. Technically, what we're doing is mostly very, very simple. Right? Most of these are expressed in basically just pure typed, sometimes first-order functional programming. And over time, we gradually shift into making that more and more true. We used to write down specifications with, funky inductive relations and beautiful type systems, what have you. Now, much more often, we're writing down functional programs that explicitly enumerate the set of transitions of the particular system right now. So that is not rocket science, and it doesn't take a long time to learn. It is a shift of emphasis. Right? So in a sense, we're writing functional programs, but we're writing very particular ones, which are specifications intended to be executable as test oracles. Right? We could have been doing that. The whole industry could have been doing that in, 1980 or 1970, pushing things a bit. Right? And it just happens that we didn't. I'm not quite sure why we didn't, but we should have been. And it's not too late to start catching up. They don't even have to be in a pure typed functional program. You could write these things in C if you didn't have any other tool in mind, as long as you were clear that this was what you were doing. By writing them in a nice way, you may enable easier verification work later, but the basic specification stuff could be done in almost anything. So it is a change of mindset. It is, in some sense, very expensive. So by normal academic, one PhD student project standards, it's very expensive. They're multi-year, multi-person exercises. But by an industry standard, this is dirt cheap. How much does it cost to build a new production file system? More than they pay us. The scale is also instructive. So this is very big by the standards of pencil and paper mathematics, and very tiny by the standards of implementation code. Right? It's big enough that you sort of have to treat it as code when you're working with it, but it's still sort of tiny. It does need, so it's very expensive by academic standards, and that's because each of these needs some significant team of people, not least so that there are several people working on the same thing who can talk about it and thereby not go mad, or at least not go mad quite so quickly. Another shift of emphasis from the academic point of view is that here we're really trying to produce models which cover the corners and which are accurate and sound for the future, not just enough to produce a paper that sounds vaguely plausible. So this is a significant shift from some parts of academia, and sometimes it causes our referees some confusion, but it has to be done. The fact that these are loose specifications is a key challenge. If we could write if we were in a deterministic world, then the spec could just be a pure functional program reference implementation, and life would be easy. You could test just by running the two things and comparing the answers. Right? But unfortunately, non-determinism is often necessary, either because there's real runtime non-determinism in the implementations, or because there are real substantially different implementations. Obviously, any non-determinism is problematic for that testing-based development cycle. Right? So software and hardware is developed by a testing process, but testing above a non-deterministic envelope is not something that we know how to do. This is very nearly the end now. It does have a big technical impact on how you express the specifications to keep that executability as a test oracle property. Things don't always work out, but Cliff, excuse me. Things don't always work out. I won't talk about these just now, but there are interesting reasons why they don't work out or could be made to work out. They work out enough to publish great papers, but they don't really work out in all cases. I think I don't have time to talk about that either. Can I talk about that? No?
Wait for the questions.
Somebody asked me a question about that. Robert, it would be good for you to ask me a question about that. So, this is the last slide. So, we've seen in the last couple of days the state of the art for verification, which has been pushed in some directions impressively far, but it's still on the scale of the stack of all the software running on that laptop, very limited, both in the scale and in the semantic features that we know how to deal with. So what I've been talking about here is sort of orthogonally pushing the world of specification to substantial aspects of the real systems, not to get full assurance, but to get some goodness. What do we need? Well, as the bare minimum, I think it's clear that if one was building any new infrastructure that has any possibility of being used by anybody, then a specification that implementations can be tested against is the bare minimum that one ought to be aiming at and is clearly easily achievable. We need sane programming languages, and this has been a failure of the PL community and of industry to get sane programming languages predominantly used. But we also need to understand that we're shifting to a world in which big, or at least moderately big, semantics is necessary. We can't do this just on the scale of a single PhD or half a PhD or a couple of papers. Any of these things involve just an amount of detail and an amount of substance that pushes them into being significantly scaled projects. And we have to somehow organize both ourselves and the funding for ourselves so that that's possible. I'll stop.
Thank you. We have time for a couple of quick questions.
Peter, you've got a slide partway in there. The writing was just too small for me to make out. Something about cherries?
Let me enlarge that slide for you, Robert, but it might not be a quick question. So, so I've been talking about the specification of artifacts, ghastly artifacts that have previously been invented. But if one tries to apply this for shiny, new, exciting, cutting-edge systems research, then it works even better. Right? So Robert and some of his colleagues have this lovely project to build one of those. Hardware capability support to make things that are actually secure. Wouldn't that be nice? Right? Or at least have some good security properties guaranteed. So they're doing hardware-software co-design for this. Right? They're building new hardware, they're porting BSD stacks and what have you, porting their C compilers, and they're using, throughout this whole project, as I understand it, as really a central tool in the design, a formal model of what the ISA is. And they're using that not principally for verification, although we are now doing some verification about it, but in these more lightweight ways. So that.
Thank you. I think in the interest of getting back on schedule, I'm going to move on. Thank you very much, Peter.